All right, good afternoon, students. I hope that everyone is doing well. Welcome to your first online NYA class. And essentially, this is the format that I'm going to be using. So what you will see, or you should be seeing through this link, is essentially the slide. And so you'll be hearing my voice, and I will be walking you through each and every slide and essentially showing you also the work step by step. So before we begin, let me just show again a few things that we've already discussed in our Zoom meeting. First of all, you have the information here, contact information in order to reach me. The easiest, however, at all times is to use Mio. I will be checking my Mio, generally speaking, every day, and I will try to respond to your Mios as quickly as possible. So this is the most efficient way to contact me. So as already discussed, in NYA, you will have 25% of the mark for lab experiments, 15% for quizzes, and again, typically quizzes will be given approximately a week or two before the exam, and this serves as an excellent preparation to see how ready you are for certain aspects of the course anyway. And for the three tests that will be worth 60% total. There will be no final exam this semester given the online context, and these are the tentative dates. These are subject to change, but they should be relatively close to this time period. Remember that you need the Chang textbook, online or paper. I always prefer paper, but that is up to you. If you have a brand new edition, that gives you the ability to connect with other resources that are useful but not necessary. Concerning the lab manual, I will be posting the lab experiments with all of the information in the days to come, one by one. So just briefly, course outline, what we are going to be looking at is essentially in Unit 1, empirical formulas, molecular formulas. We're going to be looking at significant figures. The tutorial will be on nomenclature, so this will be during the lab period for the first lab. We'll look at stoichiometry, gas laws, molarity, and this essentially will be Unit 1. Unit 2 then examines atomic theory. What is the atom? How is it understood? There's a clear connection between structure and activity. If you understand the structure of the atom properly, that should explain the reactivity. So that is an extremely important chapter. It is going to be built upon what you've already seen at the high school level, but we are going to push this much further. Unit 3 then looks at the properties of the atoms within certain families, within certain periods. And so ionization, energy, atomic size, etc., etc. So we'll get into these things more in detail when the time comes. Unit 4 is that atoms typically do not exist individually. They are bound in various types of structures. So ionic substances, covalent substances, etc., etc. Finally, Unit 5 will be looking at the forces that exist between different molecules and atoms, and so that will be a very important unit also. Unit 6 then looks at colligative properties, which is in a way a stepping stone into the next course, which will be NYB, which is the chemistry of solutions. So that, in a nutshell, is what we are going to be dealing with in this semester. So as you see, tells a very nice story, a very important story, and chemistry is about the stuff around us. Everything in the universe is made of matter and energy, and chemistry is right there at the interface of these two things. And so chemistry should be an exciting and interesting subject for all people because it relates to us in so many different ways. So I trust that you will enjoy this course. I'm going to try to make it as interesting as possible, despite the fact that we can't be face to face. Hopefully this medium will work very well for all of us. So these are the objectives for this first unit. You can go through this on your own. And essentially that brings us to our first topic, which is significant figures. When we make measurements in the context of chemistry, in the context of science, each measurement involves a certain degree of uncertainty. And so recording measurements to their appropriate accuracy is extremely important. For example, if I tell you that there's 5 milliliters, or I tell you that there's 5.5 milliliters, or I say there's 5.55 milliliters, this shows a differing level of precision. And so this is extremely important in the lab, just as units are so important. When you say I've got 5 of something, 5 what? Is it milliliters? Is it meters? Is it grams? The units are important, but also what we will call the significant figures. So significant figures reflect the accuracy or uncertainty for any given measurement. So we are going to follow specific rules in order to understand what this is all about. And by the way, you will see that in some contexts, people will use the plus minus with a certain number next to a measurement. This is not what we are going to be doing. We are going to be working exclusively with significant figures. So, non-zero numbers or integers always count as sig figs. So for example, all these numbers here will always count as sig figs. So this number here has 4 significant figures, and if you write it in with the scientific notation, the same thing is true here. You also have 5 significant figures. If you have zeros that are before the number do not count. These only indicate the magnitude of the number. For example, if I say 1 centimeter is 1 sig fig. If I say 0.01 meter, so I've just changed centimeter to meter, those zeros that are before don't increase the number of significant figures. They only indicate magnitude. Captive zeros, meaning between non-zero integers, are always significant. So this number here has 4. Trailing zeros are always significant when there is a decimal. In other words, 9.300 has 4 significant figures. Somebody might wonder, well, if it's 0, why do we write it? Well, that's the point. The point is that those zeros are telling us something. And what they're telling us is that we have a measurement that is accurate to this degree. And remember that the last number is the one that is uncertain. So this is a certain, and certain. This one here represent the one that has uncertainty. Any measurement has a certain level of uncertainty, and that's reflected in the last significant figure. When there's not a decimal, this may or may not be significant. In other words, if I write 100 in this way, how many sig figs do I have? Not clear. Some textbooks, some teachers will say 1, some will say 3. What I will say, as many textbooks do, this is ambiguous. And so we will refrain from writing numbers in this way in the context of measurements. If you want to write 100 and not use the scientific notation and show that you have 3 significant figures, all you need to do is add a dot. Adding the dot tells us that it is precise up until our last 0. So this would have 3 sig figs. Significant figures in mathematical operations. If you have certain measurements that are not measurements at all, what we would call perfect numbers or exact numbers, you do not need to use significant figures. For example, if you take a solution and you divide it in 8 vials, you know that you have 8 vials. This is not a measurement. You know that you have exactly 8 vials. And so in this context, you do not talk about sig figs. The same thing with number of days or the number of hours. These are perfect numbers. And so you can imagine this 8 as dot 0 with an infinite number of zeros. Now, in order to manipulate numbers in the context of calculations, we must follow certain rules concerning sig figs. So this part here is very important. It's pretty simple, but it's very important, and you will have to use these rules at all times when you are carrying out calculations. When multiplying or dividing, these two are equivalent for this rule, the answer should always contain the same number of sig figs as the original number that has the least amount of sig figs. For example, 2.8, 2 sig figs. 4.5039, that is 5 sig figs. When you get your final answer, you must remove all of the additional numbers that are going to be higher than the number with the lesser number of sig figs. In the same way, here we have 3 sig figs, here we have 5. We do a division, we apply the same rule. 3 sig figs is the lowest number of sig figs between these two numbers. Therefore, my answer must only contain 3 sig figs. And as you can see, those zeros before are not counted as sig figs, so it's 611. That represents our 3 sig figs. Now you see the picture of a chain here, and there's a good reason why I put that there, because there's a logic here that's very intuitive, and so I'm going to just explain this so that you can easily remember this logic. If I have a chain with 10 links, and each link is good to 1,000 pounds, but one of them is only good to 100 pounds, would you be willing to be dangled from this chain from the top of Champlain? The answer is no, unless you weigh less than 100 pounds. Because you know intuitively that even though 9 of the links are good to 1,000, one of them is weak and only allows 100 pounds of weight. And so it's the same kind of philosophy when you're dealing with sig figs. The accuracy of your final answer cannot be greater than the accuracy of your weakest number in which you do the calculations. So just remember this when you carry out calculations with sig figs. You must find the weak link, and that link will adjust the accuracy of your answer in this following way. Addition and subtraction. When adding or subtracting, the final answer should contain the same amount of decimal places as the original number, again, with the least amount of decimal places. So notice here, it's about the number of decimal places. This is the difference with addition and subtraction. So here we've got 5 sig figs, here we've got 2, and in our answer we have 3. What's going on? Well, we have 1 digit after the decimal, we have 3 digits after the decimal. This represents the one that has the least amount of decimal places. Therefore, when I give my answer, this will be my last sig fig. And whether you're doing addition or subtraction, the principle is the same. So 3 decimals, 2 decimals, my answer must have 2 decimals. Finally, rounding numbers. When the digit removed is less than 5, the preceding digit stays the same. 6.44, if I need to adjust it to 2 sig figs instead of 3, I round to 6.4. I knock off the last 4. You guys are familiar with this. This is nothing new. When the digit is removed, when the digit removed is equal or greater than 5, the preceding digit is increased by 1. So if we have 46 instead of 44, we get 6.5. Again, for 2 sig figs. If the number is 5, again, you will see that different textbook, different teachers teach different things. In my class, I will not pay attention to that. So if you've got a 5 and you want to round, I will accept either way. So that will be fine by me. Now, determine the number of sig figs in each of the following. So let's do a couple together, and then I will ask you to pause, complete the question, and then I'll go over the answers. This is the method that I'm going to be using throughout our NYA online classes. I will do some of the work, ask you to pause, ask you to do the rest of the work, and then you unpause, and that allows you to see the answers. So how many sig figs here? Well, that's easy. 2. In this case, we got a 0, but it's inside the number. That's 4. Again here, 4. So I'm going to let you do D all the way to M, and then unpause, and I'll walk you through the answers for this problem. So please pause and complete the rest of number 1. All right, so let's go through the answers. Here we have the scientific notation. 1, 2, 3, 4, that's 4 sig figs. Here the zeros before do not count. 1, 2, 3, that's our answer. Again here 3. Here we've got 7. Oh, this one is the ambiguous one. So this is one that's uncertain. We will not be using numbers in this way. In this way, it's clear that it's 3. 2, 3, 2, and 3. Problem number 2. Use the exponential notation, scientific notation, to express the number 670 to 4 sig figs. So how are we going to do this? We want to use the exponential notation. So 6 point with numbers after times 10 to the power of 2. So in this case, if you want 4 sig figs, 1, 2, 3, 4, this is how it's done. As you can see, the exponential notation is very useful in the context of sig figs, because otherwise, well, you have to use the decimal and add the 0. And when numbers are very large or very small, this method is preferred. So I'm going to ask you to do B, C, and D. So pause it, and then we'll correct. So 3 sig figs, 2 sig figs, and if we have only 1, we have to round, don't we? And so that gives us the following number. So as you can see, exponential notation, very useful in this context. Perform the following mathematical operations and express the result to the correct number of sig figs. So here we have a number, add it to this number, add it to this number, 3 decimals, 4 decimals, 1, 2, 3, 4, 5, 6 decimals. So the one that is the least is this one. So our answer must be adjusted to reflect this. Again, pause the video, complete the problem, and then unpause. So B, that gives us 2 decimals because of this number here. Now we have multiplication, 2, 4, and more than 4 sig figs. We'll have to have 2, which gives us this number. Here we divide, it's the same, and so we just adjust the last digit to reflect the rounding up. Here we have 2 operations. So what do? Well, we have to do this one first, and that gives us the following number with the right number of digits. And now we divide, and this now becomes the number of sig figs that is going to determine the number of sig figs in the final answer. This is where it gets a little bit trickier, but it's not complicated. Last, here we have this addition, subtracting calculation to do before we divide. So this gives us the following answer, and then we adjust the final answer for 4 sig figs at the end. Please note, as I should have mentioned in our Zoom meeting, that all of these slides often contain references to Chang, telling you where the material comes from in the book, and also additional problems that you could and should be doing. So you can do a lot more than what I give you, but this is just a recommendation on my part. Last thing for today. Today's class is going to be quite short. It's essentially an introduction to a few basic concepts, and essentially next class will be digging a little bit deeper in more relevant and important things. Dimensional analysis. Oh, and by the way, here are again what I just told you about, which are the extra numbers that you could and should be working on. Dimensional analysis. Hate it or love it, this is a method that we are going to be using, and you should be loving this method because it's quite simple and very useful. This essentially might replace for you what's called la règle de trois, cross multiplication. And so in this class, in all science classes, the cross multiplication method is not used. That might be a challenge for you because you might be used to using this methodology. So I'm going to teach you here dimensional analysis. Please follow carefully. This is the way that you are going to have to do this. For those of you that are wondering, what if I don't? Am I going to lose points? Well, depending on the circumstances, you might or might not. I can tell you that if there was a final exam, that would lead to removing a small deduction, a small number of marks. So please try to use this, even though I'm not going to be very strict. It is in your best interest to be doing this. So how does this work? Well, if we want to convert between days and weeks, for example, we need to find what's called the equivalency statement. And this equivalency statement allows us to change from one unit to the other. That's what dimensional analysis is all about. So we know that 1 week is equal to 7 days. And this can be expressed in two different ways. You can have 1 week divided by 7 days, which gives us 1. And of course, 1 week is equal to 7 days. So that's how you know that that number is equal to 1. So it's an equivalency statement. These two quantities, even though they're expressed with different units, they are equivalent. So if we want to convert 12 days in the number of weeks, here's how we're going to do it. You start by writing what you want to convert on the left, 12 days, and what you're looking for is a number with the unit of weeks, and that's the challenge. You start with days in your on the left, and you want to end up on the right with weeks. You can draw a little box here if you want, and that box is the equivalency statement. And you can write it 1 week over 7 days, or you could write it 7 days over 1 week. It doesn't matter. It's equal to 1 either way. However, because we start with days, days has to be on the denominator so that it cancels out when you do the operation. And week, of course, has to be on the numerator because after the operation, you must have the unit that you're looking for. So sometimes I call this the magic box, because the magic box, which contains the equivalency statement, allows you to make a unit disappear that you don't want and make the unit that you do want appear. So this is the strategy for dimensional analysis. Again, you are required to use this when you change units. Convert 15 kilometers per liter to miles per gallon, knowing that 1 gallon is equal to this many liters and 1 kilometer is equal to this many miles. So now what we're going to do is change the units using dimensional analysis. Please pause the video, try to do this using what we've just seen, and then I will correct. Alright, so we start with 15 kilometers per liter. So we want kilometer on the numerator to disappear. So that means we need to introduce miles. And we want the liter on the denominator to disappear, which means we're going to have liters on the numerator. So I'm going to start with kilometer. We've just canceled out kilometer. So we've introduced miles. And so now what we want to do is to cancel liters and to introduce gallon. So I'm going to put gallon on the bottom in my equivalency statement and the corresponding volume in liters on the numerator, so that this is going to allow liters to disappear. Finally, that gives us our answer. Are we done? No, we're not. Remember, we must respect sig figs. And here we've got 2. Therefore, our answer must be rounded to 35. And the reason I put 35 here is because I rounded my 4 to 5 and then rounded down. But it doesn't matter. Last thing for today, density. This is simply review from things that you would have seen in high school. Density is what? The amount of matter in a given volume. It's the ratio of an object's mass to its volume. So you know that iron is very dense compared to plastic, for example. That's the principle of density. In liquids, we talk about grams per milliliters. In solids, we talk about grams per cubic centimeters, and gases, grams per liters. Typically, this is how it's done. Density varies with temperature, but at a specific temperature, the density of a pure substance will not vary. It is a property of the matter. The greater the density, the greater the temperature, the lower the density. And that makes sense because molecules or atoms, as they heat up, will move at a higher rate. And so greater motion creates greater distance between the atoms or the molecules. There are exceptions, and the classic one is, of course, water. As water freezes, it actually does the opposite, which is very unusual. It's a very unusual property of water, which we will discuss in later units. So just remember that exception. So just to refresh our memories for such calculations, if we've got a water bed with the following dimensions, what mass of water does this bed contain? Knowing that the density of water is 1 gram per cubic centimeter. So again, pause, carry out the calculations, and then unpause. So, first we want to calculate the volume. And that requires having all the measurements in the same units, which gives us the following answer, which of course we have to adjust for sig figs. Don't forget, what you learned in the previous section, we must continue to apply throughout our course. Now, since this is calculated, what we can now do is to determine what is going to be the mass. And we have our formula here, density equals mass over volume. And so what we're looking for is mass. What you need to do at this point is isolate mass, solve for mass. And so since this is divided by volume, what you do is you do the opposite on one side and repeat on the other. This is basic math. If you are not comfortable with this, that means that you have to go back and review these basic principles for math. So multiply by volume on the right, multiply by volume on the left. This basically cancels out volume on the right and leads to mass equal density times volume. Multiplying the density that we have here and the volume, and it's imperative that you have the same units. Always write your units. This will avoid you making all kind of little mistakes that are unnecessary. Well, mistakes are never necessary, but that's the kind that you definitely don't want to make. So that gives you the following answer, and that's the mass of the bed. So the next class will be a tutorial, and that tutorial will only be given in the context of the lab, which if I look at my schedule here, it is going to be on Wednesday. And so I will post that on Wednesday. What I will do for your next class is jump ahead to a later slide and basically pick up from there, and the nomenclature will be seen in the lab. So there you go. That's the end of our first lesson for today. I hope that everything is clear. If you have any questions, we will be doing some problems together through Zoom during the next week. And so until then, hope everything is well, and I'll see you again soon. Have a good day.